Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring one of the universe's most mysterious and captivating phenomena, black holes. These enigmatic objects exist at the boundaries of our understanding, where space bends, time slows, and the rules of reality itself seem to transform. They are invisible yet influential, silent yet powerful, hidden yet revealed through their effects on everything around them. Black holes are not merely cosmic curiosities. They are fundamental features of the universe, shaping galaxies, directing the flow of matter, and teaching us about the very nature of existence. If you enjoy these quiet explorations, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm mysteries of black holes to carry you gently toward sleep. Let's begin. Black holes are regions where gravity becomes so strong that nothing can escape. At their most fundamental level, black holes are places where matter has collapsed into such extreme density that gravity overwhelms everything else. The pull becomes so intense that not even light, the fastest thing in the universe, can break free. This creates a boundary called the event horizon, the point of no return. Anything crossing this threshold is drawn inexorably inward, lost to the outside universe forever. Inside, the normal rules of physics begin to break down. Space and time trade places in ways that challenge our everyday understanding. Yet despite their strangeness, black holes are natural consequences of gravity, predicted by Einstein's equations and confirmed by observation. They represent the ultimate triumph of one of nature's fundamental forces, gravity taken to its absolute limit. The concept of black holes emerged from Einstein's theory of general relativity. In 1915, Albert Einstein published his general theory of relativity, describing gravity not as a force, but as a curvature of space-time itself. Massive objects bend the fabric of space around them, and other objects follow those curves. Shortly after, physicist Karl Schwarzschild found an exact solution to Einstein's equations. His solution described what would happen if all the mass of an object were compressed into an infinitely small point. The result was a region of space-time so severely warped that nothing could escape it. At first, even Einstein himself doubted such objects could truly exist in nature. They seemed too extreme, too bizarre. Yet the mathematics was undeniable. These solutions pointed towards something real, something the universe could actually create under the right conditions. It would take decades before evidence emerged, but the theoretical foundation was laid in those early years. Black holes were once called frozen stars by early theorists. Before the term black hole became standard, scientists struggled with what to call these mysterious objects. Some referred to them as collapsed stars or dark stars. Others used the phrase frozen stars because, from the perspective of a distant observer, time appears to slow and freeze at the event horizon. An object falling in would seem to take forever to actually cross that boundary, its image growing dimmer and redder, but never quite disappearing. The term black hole itself was popularized by physicist John Wheeler in 1967. It captured both the darkness of these objects and the sense that they were holes in the fabric of space. The name stuck because it conveyed the essential strangeness of these regions, places where the normal universe seemed to end and something else entirely began. Stellar mass black holes form when massive stars die in supernova explosions. Stars live by balancing two forces. Gravity pulls inward, trying to collapse the star. Nuclear fusion in the core pushes outward, providing pressure that holds the star up. For stars, much more massive than our Sun, this balance eventually fails. When such a star exhausts its nuclear fuel, there is nothing left to resist gravity's pull. The core collapses in less than a second, releasing a tremendous burst of energy. The outer layers are blown away in a supernova explosion, one of the most violent events in the cosmos. But the core continues to collapse. If it is massive enough, nothing can stop it. Neutrons cannot support it. No known force can halt the infall. The core collapses past the point of no return, forming a black hole. What remains is a region of warped spacetime, invisible but unmistakably present through its gravitational influence. The smallest black holes may weigh just a few times more than our Sun. Stellar mass black holes, formed from the deaths of individual stars, are the most common type we know of. They typically range from about 3 to several dozen times the mass of our Sun. Below 3 solar masses, the collapsing core would instead form a neutron star, held up by the pressure of neutrons packed together. But once a certain threshold is crossed, no force can prevent complete collapse. These stellar black holes are scattered throughout the galaxy, often invisible unless they happen to be feeding on nearby material. Astronomers estimate there may be millions of them in the Milky Way alone, silent remnants of stars that died long ago. Each one, a compact region of space where an entire star's worth of matter has vanished behind an event horizon. Supermassive black holes lurk at the centers of most large galaxies. While stellar black holes form from individual stars, there exists another class far more immense. Supermassive black holes contain millions or even billions of times the mass of the Sun. They sit at the hearts of galaxies, including our own Milky Way. Their origin remains mysterious. They may have formed from the merger of countless smaller black holes over billions of years. Or perhaps they arose from the direct collapse of enormous gas clouds in the early universe. Regardless of how they began, they have grown over time by consuming gas, dust, and stars. These giants shape the galaxies around them, their gravity influencing the orbits of billions of stars. They are not scattered randomly, but concentrated in galactic centers, serving as anchors around which entire galaxies rotate. Our own galaxy's center hosts a black hole millions of times the Sun's mass. Deep within the Milky Way, hidden behind vast clouds of gas and dust, lies Sgr A*, our galaxy's central black hole. It weighs approximately 4 million times as much as the Sun, compressed into a region smaller than Mercury's orbit. Though we cannot see the black hole itself, astronomers have tracked stars orbiting around it for decades. These stars move at astonishing speeds, their paths clearly shaped by an invisible massive object. In 2019, the Event Horizon Telescope collaboration captured the first image of a black hole's shadow, and later, in 2022, they imaged Sagittarius A times itself. The image showed a glowing ring of hot gas surrounding a dark center. That darkness is the shadow of the event horizon, the boundary from which nothing returns. Black holes are among the darkest objects imaginable, yet reveal themselves through light. The irony of black holes is profound. They emit no light of their own and trap any light that ventures too close. Yet they are often surrounded by some of the brightest phenomena in the universe. As matter spirals inward toward a black hole, it forms an accretion disk, a swirling ring of gas heated to millions of degrees by friction and compression. This disk glows brilliantly in visible light, X-rays, and other wavelengths. Jets of particles may also shoot outward from near the black hole at nearly the speed of light, powered by the twisting of magnetic fields. From vast distances, we see these glowing disks and jets, indirect signatures of the dark objects they surround. Black holes remain hidden, but their gravitational violence lights up the matter around them like beacons in the cosmic dark. Matter spiraling into a black hole heats up and glows across the spectrum. As gas and dust fall toward a black hole, they do not plunge directly inward. Instead, they spiral around it, forming a disk. The material in this accretion disk moves at different speeds, depending on distance from the black hole. Closer regions orbit faster, while outer regions move more slowly. This difference in speed creates friction, and that friction generates immense heat. Temperatures can reach millions or even billions of degrees. At such extremes, the disk emits radiation across the electromagnetic spectrum, from radio waves to gamma rays. The inner regions, closest to the black hole, shine brightest and hottest. By studying this light, astronomers can learn about the black hole's mass, spin, and feeding rate. The darkness of the black hole is revealed through the brilliance it creates in the material just before that material disappears. Some black holes produce jets that stretch for thousands of light years. Among the most spectacular displays in astronomy are the jets launched by black holes. Not all accreting black holes produce them, but when they do, the results are astonishing. Twin beams of particles and radiation shoot outward from near the event horizon, perpendicular to the accretion disk. These jets travel at nearly the speed of light and can extend for thousands or even millions of light years, far beyond the galaxy that hosts the black hole. The exact mechanism remains an active area of research, but it involves the black hole's rotation and the powerful magnetic fields threading through the accretion disk. These fields channel particles outward in narrow beams. When a jet points toward Earth, the black hole system can appear extraordinarily bright, classified as a blazar. Seen from the side, the jets create dramatic lobes of glowing gas. These cosmic fountains demonstrate that black holes are not merely consumers, but also powerful engines capable of influencing vast regions of space. The event horizon marks the boundary from which nothing can return. Every black hole is defined by its event horizon, an invisible spherical boundary surrounding it. This surface is not made of matter, but represents a point in space-time beyond which escape becomes impossible. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of our Sun, the radius would be about 3 kilometers. For a supermassive black hole, it could span millions of kilometers. Crossing the event horizon is a one-way journey. From the outside, you could watch as something approaches it, but you would never see it actually cross. Time dilation would stretch the image infinitely. From the perspective of the falling object, however, the crossing happens in finite time. Once inside, all paths lead inward. There is no turning back, no escape velocity fast enough, no force strong enough to reverse the fall. The event horizon is the ultimate threshold, a doorway that only opens one way. Time flows differently near a black hole's immense gravity. One of the most profound consequences of general relativity is that time itself is affected by gravity. The stronger the gravitational field, the slower time passes relative to an observer far away. Near a black hole, this effect becomes extreme. An astronaut hovering just outside the event horizon would experience time passing normally from their own perspective. But to someone watching from a safe distance, the astronaut would appear to move in slow motion. Their clock would tick more slowly. Their words would stretch out, red-shifted and slurred. At the event horizon itself, time dilation becomes infinite. To the distant observer, time appears to stop entirely. Yet, for the falling astronaut, nothing seems unusual. They cross the horizon and continue inward. This disparity reveals the deeply relative nature of time. It is not a universal constant, but something flexible, shaped by the curvature of space-time. An observer falling into a black hole might not notice crossing the event horizon. For someone falling toward a stellar mass black hole, the journey across the event horizon might be violent due to tidal forces. But for a supermassive black hole, with its much larger event horizon, the crossing could be surprisingly gentle. The curvature of spacetime would be less severe at that scale. You might pass through the boundary without any immediate indication. No wall, no barrier, no dramatic change in appearance. Only after crossing would you realize the truth. Looking outward, you might still see the universe, though distorted. Light from outside can still reach you, but any signal you tried to send back would never escape. From your perspective, the event horizon is more like a one-way mirror. You can see out, but the outside can no longer see you. The realization of your fate would come not from the crossing itself, but from the knowledge that every direction now points inward, toward the singularity. Inside the event horizon, all paths lead inexorably to the singularity. Once inside a black hole, space-time is so warped that moving toward the singularity is not a choice but an inevitability. In our everyday experience, moving forward in time is unavoidable, but we can move freely through space. Inside a black hole, the roles of space and time are reversed. The direction toward the center becomes as unavoidable as the future. No matter how you accelerate, no matter which way you fire your engines, you cannot avoid reaching the singularity. It lies not ahead of you in space, but ahead of you in time. The singularity is in your future the same way tomorrow is. This is one of the most disorienting aspects of black holes. The normal framework of existence is turned inside out, and the singularity becomes not a place but a moment, an ending that nothing can prevent. The singularity is a point where our understanding of physics breaks down. At the very center of a black hole, according to general relativity, all the matter collapses into a singularity, a point of infinite density and zero volume. Here, space-time curvature becomes infinite, and the laws of physics as we know them cease to function. Temperatures, densities, and energies reach values our equations cannot handle. This breakdown signals a limit to our current theories. General relativity predicts the singularity, but it also admits it cannot fully describe what happens there. Physicists suspect that a complete theory of quantum gravity, merging general relativity with quantum mechanics, will reveal the true nature of the singularity. Perhaps it is not a point at all, but something else, a region where space-time has a fine structure we cannot yet perceive. For now, the singularity remains a mystery hidden within a mystery. Question mark. At the heart of every black hole. Black holes are not cosmic vacuums that suck everything nearby. A common misconception is that black holes are like vacuum cleaners, pulling in everything around them. In truth, black holes obey the same gravitational laws as any other massive object. If you replace the Sun with a black hole of equal mass, Earth would continue to orbit exactly as it does now. The gravitational pull at a given distance depends only on mass, not on whether that mass is a star or a black hole. The danger arises only if you venture too close, crossing into regions where gravity becomes overwhelming. At safe distances, a black hole is no more threatening than any other massive body. Objects can orbit black holes just as planets orbit stars. Matter only falls in if it loses energy and angular momentum, spiraling inward over time. The dramatic effects occur near the event horizon, but far away, a black hole is simply a massive object sitting quietly in space. Tidal forces near a black hole can stretch objects into long strands. One of the most dramatic effects of black holes is the tidal force they exert. Gravity falls off with distance, so the side of an object closer to the black hole feels a stronger pull than the far side. For small black holes, this difference is extreme. An astronaut falling feet first toward a stellar mass black hole would feel their feet pulled much harder than their head. The differential force would stretch them out like taffy, a process gruesomely called spaghettification. Eventually, the tidal forces would tear the body apart, shredding it into atoms. For supermassive black holes, however, the tidal forces at the event horizon are much weaker because the horizon is so much larger. You could cross it intact, though you would meet your end at the singularity shortly after. Tidal forces demonstrate that gravity is not a uniform pull, but a gradient, and near black holes, that gradient becomes deadly, supermassive. Black holes have weaker tidal forces at their event horizons. This might seem paradoxical, but it is a consequence of size. The tidal force depends not on the total mass, but on how rapidly gravity changes over a short distance. For a small, stellar mass black hole, the event horizon is only a few kilometers across. The gradient is steep. For a supermassive black hole, the event horizon might span millions of kilometers. The gradient is gentle. An astronaut could cross the event horizon of a billion solar mass black hole without being torn apart. Inside, they would eventually encounter the singularity, but the initial crossing would be survivable. This gentleness is deceptive, however. It does not change the ultimate fate. Once inside, there is no escape, no matter how benign the initial experience. The larger the black hole, the more room it has to be simultaneously deadly and, initially, surprisingly gentle. Black holes slowly evaporate over unimaginable timescales through Hawking radiation. In the 1,970 seconds, physicist Stephen Hawking made a startling discovery. Using quantum mechanics, he showed that black holes are not entirely black. They emit a faint glow of radiation due to quantum effects near the event horizon. In the vacuum of space, particle-antiparticle pairs constantly appear and vanish. Near a black hole's horizon, one particle might fall in while the other escapes. To an outside observer, it appears as if the black hole is emitting radiation. This is Hawking radiation. Over vast periods of time, this process causes the black hole to lose mass and eventually evaporate. For stellar mass black holes, the timescale is incomprehensibly long, far exceeding the current age of the universe. For tiny black holes, if they exist, evaporation could happen more quickly. Hawking radiation reveals that black holes are not eternal prisons but have a finite, though extraordinarily long, lifespan. The temperature of Hawking radiation is inversely related to mass. Smaller black holes emit more intense Hawking radiation and are hotter. A black hole with the mass of the Sun would have a temperature of only a fraction of a degree above absolute zero, far colder than the cosmic microwave background. A supermassive black hole would be even colder, its temperature immeasurably small. But a hypothetical microscopic black hole would radiate intensely, glowing with high-energy particles. As a black hole evaporates, it loses mass, which makes it hotter, which causes it to evaporate faster. The process accelerates, ending in a final explosive burst of radiation. For astronomical black holes, this fate lies trillions upon trillions of years in the future, long after all stars have burned out and the universe has grown cold and dark. Hawking radiation is a whisper in the present, but will one day be the last gasp of the last black holes in existence. Black holes can spin at incredible speeds, dragging spacetime with them. A black hole is fully described by just three properties: mass, charge, and spin. Most black holes are believed to have negligible charge, leaving mass and spin as the important characteristics. When a black hole forms from a collapsing star, it typically inherits some of the star's rotation. As the core shrinks, Conservation of angular momentum causes it to spin faster, much like a figure skater pulling in their arms. The result is a spinning black hole, called a Kerr black hole. The spin drags space-time around with it in a phenomenon called frame dragging. Near the black hole, space itself is forced to rotate. A stationary observer would find themselves pulled along, unable to resist the motion. For rapidly spinning black holes, the event horizon becomes smaller, and an additional region forms called the ergosphere. Here, remaining stationary becomes impossible. Everything is dragged along with the spinning space-time. The ergosphere allows energy to be extracted from a spinning black hole. Outside the event horizon of a rotating black hole lies a region called the ergosphere. Here, space-time is dragged around so strongly that nothing can remain still relative to distant observers. Even light must move in the direction of the black hole's spin. Within this region, it is theoretically possible to extract energy from the black hole. This process is called the Penrose process, named after physicist Roger Penrose. By carefully dropping an object into the ergosphere and allowing it to split into two pieces, one falling in and the other escaping, it is possible for the escaping piece to carry away more energy than the original object had. The black hole's rotational energy is tapped. Over time, repeated extractions could slow the black hole's spin, converting its rotational energy into useful work. Advanced civilizations might one day use spinning black holes as power sources, tapping into some of the most energetic objects in the universe. Gravitational waves are ripples in space-time caused by massive, accelerating objects. When massive objects accelerate, they disturb the fabric of space-time, sending ripples outward at the speed of light. These are gravitational waves, predicted by Einstein but only directly detected in 2015. Black holes, especially when they collide and merge, are prolific sources of gravitational waves. As two black holes spiral toward each other, they radiate gravitational energy, causing their orbits to shrink. The frequency and amplitude of the waves increase, culminating in a final violent merger. The collision produces a new, larger black hole and sends a burst of gravitational waves rippling through the cosmos. These waves stretch and compress space-time itself as they pass, causing minuscule changes in distance that can be measured by sensitive instruments. The detection of gravitational waves opened a new window onto the universe, allowing us to observe events that emit little or no light. The first detected gravitational waves came from colliding black holes. On the 14th of September 2015, the LIGO detectors in the United States recorded a faint signal that would change astronomy forever. The signal lasted less than a second, but its pattern was unmistakable. Two black holes, each about 30 times the mass of the Sun, had spiraled together and merged. The collision occurred over 1 billion light-years away, yet the ripples in space-time reached Earth with enough strength to be measured. At the moment of merger, the power radiated in gravitational waves exceeded the combined light output of all the stars in the observable universe. Though it lasted only a fraction of a second, the event was cataclysmic. This detection confirmed Einstein's century-old prediction and inaugurated the era of gravitational wave astronomy. Since then, dozens of black hole mergers have been detected, each one revealing details about the population of black holes and the nature of space-time itself. Black hole mergers release energy equivalent to several suns, converted to pure waves. When two black holes merge, a portion of their combined mass is converted into gravitational wave energy. The amount can be staggering. In the first detected event, about 3 solar masses worth of energy was radiated away in less than a second. That is the equivalent of 3 suns entirely converted to gravitational waves, following Einstein's equation relating mass and energy. For a brief moment, the merger outshone the entire observable universe in gravitational wave luminosity. Yet because gravitational waves interact so weakly with matter, this torrent of energy passed through Earth and everything on it almost without effect. We felt nothing. Only the delicate laser interferometers of LIGO detected the subtle stretching and compressing of spacetime. It is a reminder that the universe is full of energies and events on scales we can scarcely comprehend, mostly invisible to us, but detectable with the right instruments. Intermediate mass black holes might fill the gap between stellar and supermassive types. For decades, black holes were thought to come in two main varieties: stellar mass black holes, formed from dying stars, and supermassive black holes at the centers of galaxies. But what about the middle ground? Intermediate mass black holes, ranging from hundreds to thousands of solar masses, have been more elusive. Some candidates have been found in dense star clusters, and gravitational wave detections have hinted at black holes in this range. How they form is uncertain. They might result from the direct collision of stars in crowded environments, or from the merger of multiple stellar mass black holes over time. They may serve as seeds for supermassive black holes, growing over billions of years through accretion and mergers. The existence of intermediate mass black holes would fill an important gap in our understanding, revealing how black holes of vastly different sizes connect across cosmic history. Primordial black holes might have formed in the early universe. Most black holes form from collapsing stars, but there is another possible origin. In the first moments after the Big Bang, the universe was extremely hot and dense. Small fluctuations in density might have led some regions to collapse directly into black holes without ever forming stars. These are called primordial black holes. They could have a wide range of masses, from microscopic to thousands of times the Sun's mass. If they exist, they have persisted since the earliest moments of cosmic history. Some physicists have speculated that primordial black holes could account for some or all of the mysterious dark matter that dominates the universe's mass. Searches for these objects continue, using gravitational lensing and other techniques. Though none have been definitively confirmed, primordial black holes remain an intriguing possibility, relics from the universe's infancy. Black holes may serve as natural laboratories for testing physics. Under extreme conditions, the environments around black holes push physics to its limits. Densities, temperatures, and gravitational fields reach values unattainable in any laboratory on Earth. By observing black holes and their surroundings, scientists can test theories of gravity, thermodynamics, and quantum mechanics in regimes far beyond everyday experience. Does general relativity hold up near the event horizon, or do deviations appear? How do magnetic fields behave in such strong gravity? What happens to matter compressed beyond nuclear densities? These are questions that black holes help answer. Gravitational wave observations, accretion disk studies, and jet analyses all provide data that constrain and refine our theories. In a sense, every black hole is an experiment conducted by nature, revealing the universe's fundamental rules. Einstein's equations permit mathematical wormholes connecting distant points in spacetime. General relativity allows for strange solutions beyond ordinary black holes. One such solution is the wormhole, a hypothetical tunnel connecting two separate regions of spacetime. Imagine spacetime folded so that two distant points nearly touch, with a throat linking them. Travel through the throat could theoretically allow journeys across vast distances, or even through time. However, such structures appear to require exotic matter with negative energy to hold them open. No such matter is known to exist in sufficient quantities. Even if a wormhole formed naturally, it would likely be unstable, collapsing before anything could pass through. Still, wormholes remain a fascinating theoretical possibility, a reminder that the mathematics of space-time contains surprises beyond what we have yet observed. The photon sphere is a region where light can orbit a black hole. Just outside the event horizon of a non-rotating black hole lies a region called the photon sphere, located at 1.5 times the radius of the event horizon. Here, gravity is so strong that light itself can be bent into a circular orbit. Photons traveling tangentially at this distance will circle the black hole indefinitely, neither falling in nor escaping. This orbit is unstable, however. The slightest perturbation will cause the photon to either spiral inward or escape outward. For observers near a black hole, the photon sphere creates strange optical effects. Light from distant objects can wrap around the black hole multiple times before reaching your eyes, creating multiple distorted images. The photon sphere is a boundary of a different kind, marking where light transitions from being able to escape to being trapped forever. Black holes are the most efficient engines for converting mass into energy. Nuclear fusion, which powers stars, converts less than 1% of mass into energy. Matter-antimatter annihilation is more efficient, converting mass entirely to radiation. But the processes around black holes surpass even this. As matter spirals into a black hole through an accretion disk, friction and magnetic forces heat it to extreme temperatures. Up to 40% of the matter's rest mass energy can be radiated away before crossing the event horizon. This makes accreting black holes among the most efficient energy sources in the universe. Quasars powered by supermassive black holes can outshine entire galaxies, fueled by this extraordinary conversion efficiency. In the distant future, advanced civilizations might harness black holes as energy sources, feeding them matter and capturing the radiated energy, using the universe's ultimate recycling system. The no-hair theorem states, black holes are remarkably simple objects. Despite forming from the collapse of complex stars with diverse compositions, black holes themselves are surprisingly simple. The no-hair theorem, proven by physicists in the 1972, states that black holes are completely characterized by just 3 properties: mass, electric charge, and angular momentum. All other information about the infalling matter, its chemical composition, its temperature, its history, is lost. 2 black holes with the same mass, charge, and spin are identical, regardless of whether they formed from hydrogen, iron, or elephants. This simplicity is both elegant and troubling. It suggests that information is destroyed when matter falls into a black hole, which conflicts with quantum mechanics. This apparent paradox, known as the black hole information paradox, remains one of the deepest puzzles in theoretical physics. The black hole information paradox challenges our understanding of physics. Quantum mechanics insists that information cannot be truly destroyed. Every process must be reversible in principle. But when matter falls into a black hole, it seems to vanish completely. The outgoing Hawking radiation appears to carry no information about what fell in, just generic thermal radiation. If the black hole eventually evaporates completely, where did the information go? This paradox has driven decades of research. Some solutions propose that information is encoded in subtle correlations in the Hawking radiation. Others suggest it might be stored on the event horizon itself, in what is called the holographic principle. Still others argue that the paradox reveals limitations in our current theories, requiring a new framework that unifies quantum mechanics and gravity. The resolution remains uncertain, But the journey toward understanding has already revealed profound insights about the nature of reality. The holographic principle suggests the universe's information is encoded on boundaries. One radical idea emerging from black hole physics is the holographic principle. It proposes that all the information contained within a region of space can be described by data on the boundary of that region. Much like a hologram encodes a three-dimensional image on a two-dimensional surface. For a black hole, the information about everything inside might be stored on the event horizon itself. The horizon's surface area, measured in Planck units, would correspond to the maximum amount of information it can hold. This principle suggests that our three-dimensional universe might be a projection of information encoded on a distant two-dimensional surface. Though speculative, the holographic principle has influenced modern approaches to quantum gravity and string theory, offering a new way to think about the fundamental structure of spacetime. Black holes might create new universes through their singularities. Some speculative theories propose that the singularities inside black holes do not simply end, but connect to new regions of spacetime. According to these ideas, each black hole might give birth to a new universe, expanding on the other side of the singularity. Our own universe might have originated from a black hole in a parent universe. This concept, while highly speculative, offers a possible explanation for the Big Bang. The intense conditions inside a black hole might trigger a bounce, transforming collapse into expansion. The new universe would be disconnected from the parent, expanding in its own dimension of time. If true, the cosmos might be a vast interconnected web of universes, each spawned from black holes in others. It is a humbling thought, suggesting that what seems like an ending might actually be a beginning. Micro-black holes could theoretically be created in particle colliders, but would evaporate instantly. When the Large Hadron Collider began operating, some speculated it might create tiny black holes during high-energy collisions. If certain theories about extra dimensions are correct, black holes could form at accessible energies. However, such micro-black holes would be incredibly small, with masses far less than a grain of sand. According to Hawking's theory, they would evaporate almost instantly, in a tiny fraction of a second, long before they could interact with surrounding matter. Rather than dangerous, these hypothetical objects would be fascinating, providing evidence for extra dimensions and quantum gravity. No such black holes have been detected, and extensive safety analyses have shown that even if they formed, they would pose no danger. The energies involved in cosmic ray collisions are far higher than anything achievable in colliders, and nature performs these experiments constantly without catastrophe. Some black holes might have electric charge, though most are thought to be neutral. The equations of general relativity allow for charged black holes, called Reissner-Nordstrom black holes, if not rotating, or Kerr-Newman black holes, if spinning. Such objects would have event horizons modified by their charge, and they could exert electromagnetic as well as gravitational forces. However, realistic black holes are expected to have negligible charge. If a black hole acquired a significant positive charge, it would quickly attract negatively charged particles from its surroundings, neutralizing itself. Similarly, a negative charge would be neutralized by positive particles. The universe contains roughly equal amounts of positive and negative charge, and matter is typically neutral. Thus, while charged black holes are mathematically possible, they are probably rare or short-lived in nature. Still, they offer interesting theoretical insights and demonstrate the richness of solutions to Einstein's equations. Naked singularities would be singularities without event horizons, visible to the outside universe. In standard black hole solutions, the singularity is hidden behind an event horizon. shielded from outside view. But some solutions to Einstein's equations allow for naked singularities, where the singularity is exposed, with no horizon to cloak it. If such objects existed, they would represent regions where the laws of physics break down, visible to the entire universe. This possibility troubles physicists because it threatens predictability. The cosmic censorship conjecture, proposed by Roger Penrose, states that nature forbids naked singularities. Any singularity that forms will always be hidden behind an event horizon. Whether this conjecture is true remains an open question. No naked singularities have been observed, and many physicists suspect that quantum effects or other mechanisms prevent them from forming. If cosmic censorship holds, it preserves the universe's causal structure and prevents unpredictability from leaking out of black holes. Rotating black holes have an inner and outer event horizon. For a non-rotating black hole, there is a single event horizon, but for a rotating black hole, the situation becomes more complex. The Kerr solution predicts two horizons, an outer event horizon, similar to the non-rotating case, and an inner Cauchy horizon, deeper within. Between them lies a region where spacetime has unusual properties. Crossing the outer horizon is still a one-way trip, but the inner horizon represents another boundary. What lies beyond it, near the singularity, is less certain. Some calculations suggest instabilities that could prevent anything from reaching the inner horizon intact. The singularity itself, in a rotating black hole, might not be a point but a ring. These features make rotating black holes even more exotic and mysterious than their non-rotating cousins. Time slows near black holes in ways that could enable time dilation journeys. The time dilation near a black hole is not just theoretical, it could have practical applications. Imagine parking a spacecraft in orbit close to a massive black hole but outside the event horizon. Time passes more slowly there than far away. While a year elapses on the spacecraft, decades or centuries could pass in the distant universe. This effect, depicted in science fiction, is real. Astronauts could travel into the far future simply by waiting near a black hole and then returning to the distant universe. Of course, the engineering challenges are immense. The spacecraft would need to survive intense gravitational forces, radiation, and debris. It would also need enormous energy to escape the black hole's pull. But the physics permits it. Black holes offer a natural mechanism for time travel into the future, turning the warping of space-time into a bridge across the ages. Black holes do not destroy matter. They transform it beyond recognition. Though we say matter is lost inside a black hole, it is more accurate to say it is transformed. The information and structure that defined the matter are erased, reduced to contributions to the black hole's mass, charge, and spin. From the outside, all complexity vanishes. Yet the mass remains, influencing the universe through gravity. Over unimaginable timescales, Hawking radiation will convert that mass back into energy, releasing it to the cosmos. In this sense, black holes are not destroyers, but transformers, taking matter in one form and eventually returning it in another. They are part of the universe's grand cycle, just like stars that fuse hydrogen into helium or supernovae that scatter heavy elements. Black holes recycle matter and energy across the longest timescales imaginable, patient agents of cosmic change. Accretion disks around black holes can shine for millions of years. When a black hole captures matter, that matter does not fall in immediately. It forms an accretion disk, a swirling, flattened structure that can persist for long periods. The disk emits radiation as matter spirals inward, and this radiation can be sustained as long as there is a steady supply of material. For black holes at galaxy centers, the fuel might come from disrupted stars, interstellar gas, or smaller galaxies merging with the host. As long as matter flows inward, the disk glows. Some active galactic nuclei, powered by supermassive black holes, have been shining for millions or even billions of years. Others flare up episodically, brightening when new material arrives, and then fading when the supply runs out. Accretion disks reveal that black holes, though extreme, participate in long-duration processes that shape galaxies over cosmic time. Tidal disruption events occur when stars wander too close to supermassive black holes. Occasionally, a star's orbit brings it too close to the supermassive black hole at a galaxy's center. When this happens, the tidal forces across the star exceed its self-gravity. The star is pulled apart, stretched into long streams of gas. Part of the material falls into the black hole, forming a temporary accretion disk, while the rest is flung outward. This event, called a tidal disruption event, produces a bright flare of light that can last for months or years. Astronomers have observed these flares in distant galaxies, catching the moment when a star meets its end. Each event offers a glimpse into the black hole's mass and properties. It also demonstrates the violence that can occur in the gravitational environments near these objects. Stars that have orbited safely for millions of years can be destroyed in minutes once they cross the fatal threshold. Binary black hole systems can orbit each other before merging. Sometimes, two black holes find themselves in orbit around a common center, forming a binary system. This can happen when two galaxies merge, bringing their central black holes together, or when two massive stars in a binary system both collapse into black holes. Once paired, the black holes spiral slowly inward, losing energy to gravitational waves. Over millions or billions of years, their orbits shrink. Eventually, they circle each other hundreds of times per second before merging in a cataclysmic collision. The final moments, called the ringdown, involve the newly formed black hole vibrating and settling into a stable state, emitting the last burst of gravitational waves. Each binary black hole merger adds to our catalogue of observations, helping astronomers understand how often such events occur and how black holes grow over cosmic history. Gravitational lensing around black holes bends light in spectacular ways. Black holes, like all massive objects, bend the path of light passing nearby. This effect, called gravitational lensing, becomes extreme near a black hole. Light from a distant star can be bent around the black hole, producing multiple distorted images. If a background star aligns perfectly, the light wraps around the black hole in all directions, forming a ring called an Einstein ring. The black hole itself remains dark, but the lensed light creates halos and arcs. Observers near a black hole would see the entire sky distorted, with stars smeared and duplicated. The event horizon would appear as a dark circle, surrounded by glowing, bent light. These effects have been observed in simulations and calculations. The 2019 image of the black hole in M87 showed a bright ring of emission, partially produced by lensed light circling the event horizon. The shadow of a black hole is larger than the event horizon itself. When we speak of imaging a black hole, what we actually see is its shadow. This shadow is the dark region formed by photons that approach close enough to be captured. For a non-rotating black hole, the shadow is about 2.6 times the radius of the event horizon. This is because the photon sphere, where light can orbit, lies at 1.5 times the event horizon radius, and the shadow's edge corresponds roughly to this region. The shadow appears against a background of glowing material, often the accretion disk or surrounding gas. Measuring the shadow's size tells astronomers the mass of the black hole. The first black hole shadow imaged was of the supermassive black hole in the galaxy M87, followed by Sagittarius A times in our own galaxy. These observations confirmed predictions from general relativity and gave us the first direct visual evidence of event horizons. Black holes challenge the very concept of before and after inside the horizon. Inside the event horizon, time and space exchange roles, in a sense. The singularity is not a place in space, but a moment in time. This makes causality inside a black hole profoundly strange. Every event inside leads inexorably to the singularity. There is no before and after in the usual sense, because all paths converge to the same endpoint. The future is the singularity, unavoidable. For an outside observer, watching something fall in, the object's time appears to slow and freeze at the horizon. But for the infalling object, time continues. The clash between these perspectives reveals the relativity at the heart of Einstein's theory. Time is not a universal stage on which events occur, but something deeply tied to the observer's path through spacetime. Black holes push this truth to its extreme conclusion. The universe might be filled with many more black holes than we know. Most black holes are invisible, detectable only through their effects. Stellar mass black holes that are not feeding on nearby matter emit no light. They are silent, dark objects scattered through the galaxy. Astronomers estimate that the Milky Way alone hosts tens of millions of stellar mass black holes, but only a few dozen have been directly observed. Most are found when they are part of binary systems, pulling matter from a companion star. Isolated black holes remain hidden. Advances in gravitational wave astronomy are revealing more, catching them when they merge, and gravitational microlensing, where a black hole briefly magnifies a background star, offers another detection method. As technology improves, we will likely discover that black holes are far more common than currently catalogued, a dark population woven throughout the fabric of galaxies. Black holes can exist in almost any mass, from microscopic to billions of solar masses. In principle, black holes can have almost any mass. The smallest theoretically possible black hole, called a Planck mass black hole, would weigh about 22 micrograms and be smaller than a proton. Such tiny black holes would evaporate via Hawking radiation in a fraction of a second. At the other extreme, the largest known black holes weigh tens of billions of times the Sun's mass, lurking at the centers of massive galaxies. Between these extremes, nature has crafted black holes across a vast range. Stellar mass black holes typically weigh several to a few dozen solar masses. Intermediate mass black holes span hundreds to thousands of solar masses. Supermassive black holes range from millions to billions. This spectrum reveals that black holes are not rare oddities, but versatile outcomes of gravitational collapse, scalable across an enormous range of sizes. The closest known black hole is only about 1,000 light-years away. For many years, the nearest known black hole was thought to be several thousand light-years distant, but recent discoveries have found candidates much closer. One system, called HR 6819, was initially reported to host a black hole only about 1,000 light-years from Earth. Later analysis has cast doubt on this claim, and the nearest confirmed stellar mass black hole remains somewhat farther, but the search continues. The nearest supermassive black hole, of course, is Sagittarius A times at the center of our galaxy, about 26,000 light-years away. As surveys improve and more binaries are studied, it is likely that closer black holes will be found. They are out there, invisible in the night, passing through the galaxy unseen. One might be closer than we realize, a dark companion traveling silently among the stars. Black holes are among the longest-lived objects in the universe. Stars burn out, planets cool, galaxies disperse. But black holes endure. Once formed, a black hole will persist essentially unchanged for timescales that dwarf the current age of the universe. A stellar mass black hole would take roughly 1067 years to evaporate via Hawking radiation. A supermassive black hole could last 100 years or more. These numbers are so vast, they defy comprehension. By the time black holes evaporate, the universe will have entered an unimaginably different era, with all stars long dead, galaxies dissolved, and only black holes evaporating particles, and darkness remaining. In the final epoch of the universe, black holes will be the last massive structures, slowly dissolving into the void. They are the cosmos's ultimate survivors, patient witnesses to the end of time. Studying black holes helps us understand the structure of spacetime. Black holes are not just exotic objects of curiosity. They are essential tools for exploring the foundations of physics. They probe the limits of general relativity, testing Einstein's theory in the most extreme conditions. They reveal the interplay between gravity and quantum mechanics, highlighting the need for a unified theory. They challenge our understanding of information, causality, and the nature of time. Each black hole observation, whether through gravitational waves, electromagnetic radiation, or direct imaging, adds a piece to the puzzle. The more we learn about black holes, the more we learn about the fabric of reality itself. They are laboratories provided by nature, experiments we could never conduct ourselves, offering insights into questions that reach to the very core of existence. Black holes might eventually reveal the theory of quantum gravity. For a century, physicists have sought a theory that unifies quantum mechanics and general relativity. Black holes are the arena where these two pillars of physics collide. Quantum mechanics governs the very small. General relativity describes the very massive. At the singularity of a black hole, both regimes meet. Quantum effects should become important where space-time curvature is extreme. Hawking radiation already hints at this intersection. The black hole information paradox forces physicists to confront the conflicts between the theories. Solutions involving string theory, loop quantum gravity, or other frameworks all try to describe what happens at the Planck scale, where quantum gravity dominates. Black holes, by their very nature, demand this deeper theory. They are signposts pointing toward the next revolution in physics. Black holes create extreme environments that stretch our imagination. Trying to visualize the interior of a black hole is nearly impossible. Our everyday intuition fails. Space and time behave in ways utterly alien to experience. Light cannot escape. All paths lead to the singularity. The singularity itself is a breakdown of our models. Yet, despite these challenges, black holes are real, confirmed by observation. They exist in our universe, governed by the same laws that govern everything else, simply pushed to the extreme. This duality, the familiar and the utterly strange, is one of the deepest mysteries. Black holes remind us that the universe is larger, stranger, and more wondrous than our minds can easily grasp. They humble us, showing that reality extends far beyond the realm of human experience, into territories where mathematics and physics become our only guides. Ancient philosophers speculated about objects so dense nothing could escape. Long before Einstein, thinkers pondered dense objects. In the 18th century, John Michel and Pierre-Simon Laplace imagined stars so massive that their escape velocity exceeded the speed of light. They called them dark stars, objects that would be invisible because light could not leave them. Though their reasoning was based on Newtonian physics, which does not fully apply, the intuition was correct. The concept of a dark star anticipated black holes by over a century. It shows that the human mind, even without modern tools, can glimpse deep truths through logic and imagination. These early ideas, though incomplete, planted seeds that would grow into our current understanding. They remind us that science is a continuous journey, with each generation building on the insights of those before. Black holes are not doorways to other places, but endpoints of spacetime. Science fiction often portrays black holes as portals to other universes or distant parts of space, while wormholes, if they exist, might serve such a function. Real black holes do not. A black hole is an endpoint, not a passage. Once you cross the event horizon, your journey ends at the singularity. There is no emerging elsewhere. The singularity represents the limit of space-time in that direction. It is an edge, a boundary, where the known laws cease. While speculative theories propose exotic possibilities, observations and tested physics point to black holes as terminal regions. They are fascinating, not because they lead somewhere else, but because they represent the ultimate consequence of gravity. They are the universe saying, "Here, space and time come to an end." The sound of merging black holes was converted from gravitational waves. When LIGO detected gravitational waves from merging black holes, scientists converted the data into sound. The rising pitch and final burst, known as a chirp, could be played through speakers. Though gravitational waves are not sound waves and propagate through space-time rather than air, the analogy helps humans perceive the event. The chirp rises in frequency as the black holes spiral faster, culminating in a brief, sharp peak at merger, followed by the ring-down as the final black hole settles. Each black hole merger has a slightly different chirp, depending on masses and spins. Listening to these gravitational wave signals offers a new way to experience the universe, turning invisible space-time ripples into audible phenomena. It is a reminder that the cosmos is full of events that, with the right tools, we can sense in unexpected ways. Black holes might hold clues to the ultimate fate of the universe. The universe's fate depends on the balance of matter, energy, and the expansion rate. If the universe continues expanding forever, it will eventually cool and darken in a scenario called the Big Freeze or heat death. In this far future, black holes will be among the last remaining structures. Over incomprehensible timescales, they will evaporate via Hawking radiation, releasing their energy back to the void. The final black holes will disappear, leaving only a thin gruel of particles and radiation, spreading ever farther apart. The universe will approach a state of maximum entropy, with no structure, no stars, no galaxies, just emptiness. Black holes, as the longest-lived massive objects, will witness nearly the entire story of the cosmos before they too fade. They are the last chapter in the book of the universe's history. Some scientists propose black holes as dark matter candidates. Dark matter, the invisible substance that dominates the universe's mass, remains unidentified. Could some of it be black holes? Specifically, primordial black holes formed in the early universe might contribute. These would be difficult to detect directly, especially if they are small. Gravitational lensing and other indirect methods can place constraints on their abundance. Current evidence suggests that primordial black holes, if they exist, cannot account for all dark matter, but they might make up a fraction. The idea is attractive because it invokes known physics rather than hypothetical particles. However, most physicists favor the particle explanation for dark matter, with black holes playing at most a minor role. Still, the question remains open, and ongoing searches continue to refine our understanding of what dark matter truly is. The extreme gravity of black holes warps light into rings and arcs. Observers near a black hole would see the sky transformed. Stars would not be in their usual positions. Light bending around the black hole would distort constellations, stretching and wrapping them. The event horizon itself would appear as a dark disk, surrounded by multiple rings of light from photons that have orbited the black hole one or more times before escaping. Behind you, the sky would appear compressed, with more stars visible in a smaller area. Ahead, near the black hole, strange distortions would dominate. If the black hole was spinning, the light would be further twisted by frame-dragging effects. Visiting such a place, if it were possible, would be profoundly disorienting. The universe you know would be bent and folded, a demonstration that space itself is not a fixed stage, but a flexible medium, shaped by mass and energy. Black holes inspire questions about the origin and structure of reality. Why do black holes exist? What purpose do they serve, if any? These are not questions physics alone can answer, but they linger in the minds of those who study these objects. Black holes represent extremes: maximum density, ultimate gravitational pull, the boundary of spacetime. They seem almost designed to challenge our understanding, to force us to confront limits. Perhaps black holes are the universe's way of revealing its deeper structure. By pushing physics to breaking points, they highlight where our theories need refinement. Or perhaps they are simply inevitable consequences of the laws of nature, as unavoidable as stars or galaxies. In either case, they stand as monuments to the strangeness and beauty of the cosmos, reminding us that reality is richer and more intricate than we can easily imagine. Black holes connect to some of the deepest questions in philosophy. What is the nature of time? Can information truly be destroyed? What does it mean for something to exist if it is hidden behind an event horizon? Black holes touch on questions that have intrigued philosophers for millennia. They exist at the intersection of science and metaphysics, places where empirical observation meets conceptual mystery. The fact that we cannot see inside a black hole raises epistemological questions. How do we know what is there? The fact that time behaves strangely near them challenges our intuitions about reality. Black holes force scientists and thinkers to grapple with the limits of knowledge and the structure of existence. They are not just objects to be studied, but phenomena that provoke reflection on the fundamental nature of the universe and our place within it. The universe's black holes are relics and engines of cosmic history. Every black hole tells a story. A stellar mass black hole marks the death of a massive star, an event that seeded space with heavy elements and energy. A supermassive black hole traces the growth of a galaxy over billions of years, accumulating mass through countless mergers and accretion events. Intermediate mass black holes hint at processes in dense stellar clusters or primordial fluctuations. Together, the population of black holes forms a record of the universe's violent and creative history. They are both endings and beginnings, destroyers and builders. By studying them, we read the biography of the cosmos, learning how structure formed, how stars died, how galaxies evolved. Black holes are not footnotes, but central characters in the ongoing story of creation. Black holes teach us that the universe is governed by laws we can understand. Despite their strangeness, black holes obey precise, mathematical laws. They are solutions to Einstein's equations, predictable and calculable. Their behavior follows thermodynamic principles. Their radiation conforms to quantum mechanics. This is one of the most hopeful lessons black holes offer. Even at the extremes, the universe is lawful. We are not confronted with chaos, but with complexity that yields to patient study. Our minds, evolved on a small planet, can nonetheless grasp the behavior of objects billions of light years away, or the conditions inside event horizons. This is a triumph of human thought. Black holes, far from being incomprehensible, are comprehensible. They are difficult, yes, but knowable, and that knowability speaks to the deep unity and elegance of physical law. Observing black holes requires international collaboration and ingenuity. The Event Horizon Telescope, which captured the first black hole images, was not a single instrument, but a network of radio telescopes spanning the globe. Data from sites in Hawaii, Chile, Arizona, Spain, and Antarctica were combined, effectively creating an Earth-sized telescope. Coordinating observations, synchronizing atomic clocks, transporting petabytes of data, and processing the signals took years of effort by hundreds of scientists. Gravitational wave detectors like LIGO and Virgo similarly represent massive collaborative efforts involving thousands of researchers. Black hole science is too vast for any one person or nation. It requires the pooling of resources, expertise, and vision. In this way, black holes bring humanity together, uniting us in a shared quest to understand the cosmos. They remind us that the greatest achievements come not from isolation, but from cooperation. The future will bring even more detailed observations of black holes. The next generation of gravitational wave detectors will be more sensitive, detecting mergers farther away and with greater precision. Space-based observatories like LISA, planned for the 2030 seconds, will observe gravitational waves from supermassive black hole mergers, events inaccessible to ground-based detectors. Improved radio telescope networks will image black hole shadows with higher resolution, revealing details of the accretion flow and magnetic fields. X-ray missions will study the innermost regions of accretion disks, measuring the spin of black holes and testing relativity. Each advance will refine our picture, turning black holes from mysterious silhouettes into well-characterized objects. The coming decades promise a golden age of black hole astronomy, where observations keep pace with theory, and the universe's darkest objects are illuminated by human ingenuity. Black holes remind us that endings can be beginnings in disguise. The death of a star in a supernova gives birth to a black hole. The black hole, over eons, may power jets and winds that trigger star formation in surrounding gas. Its gravity helps bind galaxies together. In the distant future, its evaporation will return energy to the universe. What seems like an end, the collapse into a singularity, is also a transformation, a rearrangement of matter and energy into new forms. This cycle mirrors the broader rhythms of the cosmos, where nothing is ever truly lost, only changed. Black holes are not voids of nothingness, but active participants in the cosmic dance. They teach us that even in the darkest, most extreme places, there is process, change, and connection. Endings and beginnings are two faces of the same coin, woven together in the fabric of spacetime. The study of black holes is a testament to human curiosity and courage. To investigate black holes requires venturing into realms of thought far from everyday experience. It demands grappling with abstract mathematics, counterintuitive physics, and scenarios that stretch the imagination. It requires building instruments of staggering sensitivity, analyzing vast datasets, and testing theories against the slimmest of signals. Yet humans do this willingly. Driven by the desire to understand, we have detected the whisper of merging black holes from over 1 billion light-years away. We have imaged the shadow of an event horizon. We have peered into the heart of our own galaxy and seen the invisible. This is not just science. It is an expression of who we are. Creatures who look up, who wonder, who refuse to accept mystery without investigation. Black holes, in all their strangeness, call out the best in us. In the silence of the cosmos, black holes wait. They do not call out. They do not shine with their own light. They are patient, silent, shaping space around them through gravity alone. Some have waited billions of years, spinning quietly in the dark. Others formed recently, still settling from the violence of their birth. They are scattered across the universe, from the hearts of galaxies to the lonely spaces between stars. Invisible, yet present. Hidden, yet influential. They wait for us to find them, to study them, to learn from them. And as we do, they reveal secrets about the nature of reality, about time, space, and existence itself. In their silence, they speak volumes. In their darkness, they illuminate the deepest questions we can ask. Black holes reveal that the universe operates on scales beyond human comprehension. When we consider the masses involved, millions or billions of times that of our Sun, compressed into regions smaller than our solar system, the numbers become abstract. Our minds evolved to understand the scale of our immediate environment, the sizes of animals, the distances we could walk, the time between seasons. Black holes exist on scales so far removed from this that we must rely entirely on mathematics and indirect observation. Yet even though we cannot directly experience them, we can understand them. This gap between experience and understanding is one of the remarkable features of modern science. We extend our senses through instruments and our intuition through theory, reaching toward objects and phenomena that would otherwise remain forever beyond our grasp. The history of black hole discovery spans centuries of human thought. From the early speculations about dark stars to Einstein's relativity, from Schwarzschild's solution to Hawking's radiation, the story of black holes intertwines with the story of physics itself. Each generation built upon the work of the previous, refining concepts, making predictions, and eventually confirming them through observation. The journey was not straight. There were wrong turns, dismissed ideas that later proved correct, and fierce debates about whether such objects could truly exist. But gradually, through persistence and ingenuity, the picture clarified. Today, we do not merely speculate about black holes. We observe them, measure them, and use them to test our deepest theories about reality. This progression from hypothesis to confirmed fact demonstrates the power of the scientific method and the cumulative nature of human knowledge. Black holes exist in nearly every large galaxy we can observe. As surveys have improved and more galaxies have been studied, a clear pattern has emerged. Essentially, every massive galaxy hosts a supermassive black hole at its center. The mass of these black holes correlates with properties of their host galaxies, suggesting a deep connection between black hole growth and galaxy evolution. This relationship hints that black holes are not mere byproducts, but integral components of cosmic structure. They may regulate star formation by heating gas through their jets and winds. They may influence the distribution of matter through their gravity. The presence of these giants at galactic centers transforms our view of galaxies themselves. They are not just collections of stars, but complex systems with central engines that shape their development over billions of years. Binary supermassive black holes are expected, but difficult to observe. When two galaxies merge, their central black holes should eventually form a binary system. These pairs would orbit each other for millions of years before finally coalescing. Detecting such systems is challenging because the orbital periods are long and the separations are small on astronomical scales. However, astronomers have found candidates through various methods. Some show periodic variations in brightness, possibly from the binary orbit. Others show unusual jet structures that might result from precession caused by a companion. Gravitational wave observatories like LISA will eventually detect the final mergers of these supermassive pairs, opening a new window on galaxy evolution. Each detection will provide evidence for how galaxies merge and how their central black holes grow through cosmic time. The cosmic censorship hypothesis protects the predictability of the universe. If naked singularities could exist, visible to the outside universe without event horizons, they would represent regions where physics breaks down in ways observable to all. Light cones, the structures that define causality, could become ill-defined. Events might occur without predictable causes. The cosmic censorship hypothesis, proposed by Roger Penrose, states that nature prevents this. Singularities, if they form, are always hidden behind event horizons, protecting the rest of spacetime from their pathologies. While not proven, this conjecture seems to hold in all realistic scenarios studied. It reflects a deep hope that the universe, however strange, remains fundamentally knowable. Even at its most extreme points, cause and effect persist, and the laws of physics continue to operate, shielded from chaos by the event horizons that cloak the most violent breakdowns of spacetime. Quantum mechanics may resolve the singularity into something finite. Classical general relativity predicts singularities of infinite density at black hole centers, but physicists suspect this is an artifact of ignoring quantum effects. At the Planck scale, quantum fluctuations of spacetime itself become important. Some approaches to quantum gravity, such as loop quantum gravity, suggest that the singularity might be replaced by a region of extremely high but finite curvature. Others propose that information about the collapsing matter is preserved in subtle quantum correlations. String theory offers its own perspectives, with possibilities like fuzzballs, where the event horizon region is not empty but filled with quantum strings. These ideas remain speculative, awaiting a complete theory, quantum gravity. But they share a common theme: the singularity, that point of infinite density predicted by classical theory, might not exist in the final, complete description of nature. Black holes might be keys to understanding the arrow of time. Time flows in one direction, from past to future. Entropy, a measure of disorder, tends to increase. This is the second law of thermodynamics, one of the deepest principles in physics. Black holes have entropy proportional to the area of their event horizons, a result discovered by Jacob Bekenstein and Stephen Hawking. This black hole entropy is enormous, suggesting that black holes are highly disordered states. When matter falls into a black hole, the universe's total entropy increases. As black holes evaporate via Hawking radiation, they release this entropy back into space. The connection between black holes, entropy, and thermodynamics hints at deep links between gravity, quantum mechanics, and the flow of time itself. Understanding these connections might reveal why time has an arrow, why the past is different from the future, and how the initial low-entropy state of the universe has evolved into the complex, high-entropy cosmos we see today. Every black hole contains a record of its history encoded in its properties. Though black holes are simple in the sense of the no-hair theorem, having only mass, spin, and charge, these properties tell a story. A rapidly spinning black hole suggests it formed from a rotating progenitor or has accreted matter in an organized way. A slowly spinning one might have grown through chaotic mergers from multiple directions. The mass reveals the black hole's accumulated history of consumption. Supermassive black holes with billions of solar masses have been feeding for billions of years, swallowing gas, dust, and stars. Each black hole is a fossil record of the violent processes that formed and grew it, a compressed archive of cosmic violence and transformation. By measuring these properties across populations of black holes, astronomers reconstruct the history of galaxies, star formation, and the large-scale structure of the universe. Black holes challenge the notion of what it means to exist. Consider a black hole that formed billions of years ago. The matter that created it collapsed past the event horizon long ago, hidden from the outside universe. Does that matter still exist? In what sense? The outside universe interacts only with the black hole's gravitational field, which extends outward but reveals nothing about the interior. Philosophically, this raises questions about existence and observation. If something is forever hidden, does it still exist in a meaningful way? Modern physics suggests that information is preserved, somehow encoded in the Hawking radiation or on the event horizon. But the classical picture, where the matter simply disappears behind a boundary, troubles our intuitions. Black holes force us to confront the limits of observation and the nature of reality itself. They are not just objects but puzzles that probe the foundations of ontology. The temperatures inside black holes are beyond anything we can easily describe. As you approach the singularity inside a black hole, tidal forces grow without bound. These forces would heat matter to unimaginable temperatures before tearing it apart completely. Near the singularity, space-time curvature becomes so extreme that describing temperature in the usual sense breaks down. The very concepts of hot and cold require a stable reference frame and thermal equilibrium, neither of which exist in such an environment. The violence of the singularity transcends ordinary descriptors. It is not merely hot or dense, but represents a condition where the usual vocabulary of physics fails. This failure is not a defeat, but a signpost, indicating where new physics must emerge, where a deeper theory will replace our current incomplete understanding. Black holes might outlast every other structure in the cosmos. In the far future, after all stars have burned out and all planetary systems have decayed, black holes will remain. They will be the dominant objects in a dark, cold universe. Slowly, over timescales that make the current age of the universe seem like an eye blink, they will evaporate. Smaller black holes will vanish first, over 67 years or so. Larger ones will persist longer, with the supermassive giants lasting beyond 100 years. In this final era, the universe will be nearly empty, with evaporating black holes as the last remnants of structure. When the final black hole evaporates, the universe will be left with only a thin soup of particles, expanding forever, approaching a state of maximum entropy and ultimate stillness. Black holes will have been the last witnesses to the age of structure, the final monuments to the cosmos's creative epoch. Imagining life near a black hole stretches our conception of habitability. Could life exist near a black hole? The environments are extreme, with intense radiation, tidal forces, and energetic jets. But in the outer reaches, beyond the immediate danger zones, conditions might be less hostile. A planet orbiting at a safe distance from a supermassive black hole could potentially be stable, warmed by the accretion disk's glow, rather than a star. The time dilation would mean that less time passes for inhabitants than for the distant universe, but within their own reference frame, life would proceed normally. Energy could be abundant, harvested from the accretion disk or the black hole's spin. Such scenarios remain speculative, and we have no evidence of life in such environments. But they illustrate that black holes, despite their reputation as destroyers, might also be sources of energy and stability in the right circumstances. The mathematics of black holes is both beautiful and challenging. The equations describing black holes involve tensor calculus, differential geometry, and concepts from advanced physics. Yet within this complexity lies elegance. The Schwarzschild solution is remarkably simple for such an extreme object. The Kerr solution, describing rotating black holes, is more complex, but still exact and beautiful. These solutions reveal deep symmetries in the laws of nature. They show that Einstein's field equations, a set of 10 coupled non-linear differential equations, can be solved exactly in certain cases. Working through the mathematics of black holes is a journey into one of physics' most sophisticated achievements, where geometry and gravity merge, and space-time becomes a dynamic, responsive fabric shaped by mass and energy. Black holes unify concepts from across physics. They connect general relativity with thermodynamics through black hole entropy. They link gravity with quantum mechanics through Hawking radiation. They touch on statistical mechanics, information theory, and even holography. No other objects in physics bring together so many disparate ideas. This unifying role makes black holes central to modern theoretical physics. They are testing grounds where different frameworks meet and must be reconciled. Progress in understanding black holes often leads to progress in understanding fundamental physics more broadly. They are nexuses where multiple threads of thought converge, and working on black holes means engaging with some of the deepest questions in all of science. The first image of a black hole shadow was a triumph of technology and coordination. When the Event Horizon Telescope released the image of M87's black hole in April 2019, the world saw something never before glimpsed: the shadow of an event horizon. The image showed a bright ring of light surrounding a dark center, exactly as theory predicted. Achieving this required synchronizing observations from telescopes around the world, effectively creating an Earth-sized aperture. Atomic clocks kept precise time. Petabytes of data were recorded on hard drives and physically transported for processing. Sophisticated algorithms reconstructed the image from the sparse data. The result was a blurry ring, but within that blur was confirmation. Black holes are real. Event horizons exist. Einstein's equations hold even in the most extreme environments we can observe. The image was a monument to human ingenuity and our drive to see the unseeable. The second black hole image, of Sagittarius A*, was even more challenging. Our galaxy's central black hole, Sagittarius A*, is much closer than M87's, but also much smaller in mass. This means the accretion disk around it changes on timescales of minutes, not days. During the hours of observation required to synthesize an image, the structure was evolving. This made imaging far more difficult. Astronomers had to develop new techniques to account for the variability, essentially averaging over the fluctuations to reveal the underlying structure. The result, released in May 2022, showed a similar ring to M87, confirming that our own galaxy hosts a supermassive black hole. Seeing the shadow of Sagittarius A times felt more intimate, more immediate. This was our black hole, the one at the heart of our stellar home, finally revealed. Black holes are subjects of intense, ongoing research across many fields. Observational astronomers search for new black holes and characterize known ones. Gravitational wave physicists analyze merger events and extract information about populations and cosmology. Theoretical physicists work on quantum gravity, information paradoxes, and the nature of singularities. Numerical relativists simulate black hole collisions on supercomputers. Astrophysicists model accretion disks, jets, and the interaction between black holes and their environments. Each subfield contributes pieces to the larger puzzle. Conferences bring together researchers from these diverse areas, fostering collaboration and cross-pollination of ideas. The study of black holes is a vibrant, active field, with new discoveries and theoretical insights emerging regularly. It is a testament to how much there is still to learn, even a century after the basic concept was first formulated. Black holes teach humility about the limits of human perception. Our senses evolved to detect visible light, sound, heat, and other phenomena relevant to survival on Earth. Black holes emit none of these in ways we can directly perceive. We cannot see them with our eyes, hear them with our ears, or feel them with our hands. To detect them, we must build instruments that extend our senses: radio telescopes, X-ray detectors, gravitational wave interferometers. We must learn to translate data into understanding, to see patterns in numbers, to hear chirps in gravitational wave signals. This process of extended cognition, where tools and theories become extensions of our minds, is how modern science operates. Black holes remind us that the universe does not care about our limitations. It will reveal its secrets only to those willing to look beyond the narrow window of direct human perception. The universe's black holes are connected through the cosmic web. Galaxies are not isolated islands, but nodes in a vast network of filaments and voids. Gas flows along these filaments, funneling material toward galaxies and their central black holes. When galaxies collide, their black holes merge, sometimes being ejected from their hosts and wandering through intergalactic space. The gravitational influence of black holes shapes the large-scale structure, while the structure itself determines where and how black holes form and grow. This interconnectedness means that understanding black holes requires understanding cosmology, and vice versa. They are local objects with cosmic implications, tied into the fabric of the universe's evolution from the Big Bang to the present and beyond. Fictional depictions of black holes range from accurate to wildly imaginative. Science fiction has embraced black holes as plot devices, gateways, weapons, and mysteries. Some portrayals are grounded in real physics, like the film Interstellar, which consulted physicists to render realistic visuals of a black hole and its effects. Others take liberties, treating black holes as wormholes or using them as dramatic backdrops without concern for accuracy. These fictional treatments, even when inaccurate, serve a purpose. They capture public imagination and inspire curiosity. Many physicists trace their interest in black holes to childhood encounters with science fiction. The interplay between fiction and science is productive, with each informing the other. Fiction asks, "What if?" And science answers, "Here's what would actually happen," enriching both the stories and our understanding. Black holes are natural consequences of the universe's laws, not aberrations. They are not glitches or mistakes, but inevitable outcomes when matter collapses under gravity. Given the laws of physics as we know them, black holes must exist. Stars above a certain mass cannot avoid forming them. Quantum fluctuations in the early universe might have seeded them. The mathematics demands their existence. This inevitability suggests that black holes play a necessary role in the cosmos. Perhaps they are essential for regulating galaxy growth, or for recycling matter and energy, or for some purpose we have not yet understood. They are woven into the fabric of reality, as much a part of the universe as stars, planets, and light itself. To understand the cosmos fully, we must understand black holes. There is no complete picture of the universe that does not include them. The journey to understand black holes continues with each new generation. Students today learn about black holes as established facts, but there is still much to discover. Each cohort of scientists brings fresh perspectives, new questions, and innovative techniques. The questions evolve from "Do black holes exist?" to "How do they form and grow?" to "What happens at the Singularity? And how do they connect to quantum gravity?" Each answer breeds new questions, pushing the frontier of knowledge outward. The study of black holes will likely occupy researchers for centuries to come, as new instruments reveal finer details and deeper theories emerge to explain them. Young people today might be the ones to solve the information paradox, image the event horizon in exquisite detail, or detect the first primordial black hole. The story is far from over. Black holes inspire awe in ways that transcend scientific understanding, even for those who do not grasp the mathematics or the physics. The concept resonates. A place where time stops, where gravity is so strong nothing escapes, where the very fabric of space is torn. These ideas carry a mythic quality, evoking the sublime, the terrifying, and the wondrous. Black holes have entered popular culture as symbols of mystery, power, and the unknown. They appear in art, music, literature, and philosophy. This cultural resonance is important. It shows that black holes touch something deep in human consciousness, a fascination with boundaries, with endings, with the places where the familiar gives way to the alien. They are scientific phenomena, yes, but also cultural artifacts, symbols through which we explore our relationship with the universe. The silence of space near a black hole is profound beyond earthly quiet. In the vacuum of space, there is no air to carry sound. Near a black hole, in addition to this silence, there is often a lack of nearby matter. You might be surrounded by the void, with only the distant glow of the accretion disk or the warped starlight. The silence would be absolute, broken only by the hum of your own spacecraft or the beating of your heart. This quietness contrasts with the violence occurring just meters away, where matter is torn apart and space-time is twisted. It is a stillness that contains potential, a calm before the inevitable fall. In this silence, there is space to think, to reflect, to feel the weight of existence at the edge of the ultimate boundary. It is a meditative stillness, charged with the presence of the most extreme gravity in the known universe. Black holes do not hunger or desire, they simply exist. It is tempting to anthropomorphize black holes, to describe them as devouring or consuming, but they are not alive. They have no intentions, no malice, no consciousness. They are concentrations of mass, warping space-time according to mathematical laws. Matter falls into them, not because they pull it in with purpose, but because that is what gravity does. The language we use, speaking of black holes feeding or growing, is metaphor, a convenient shorthand. The reality is more austere. A black hole is a region of space-time with certain properties, existing passively, responding only to the matter and energy in its vicinity according to the impartial laws of physics. This lack of intent makes them no less fascinating. If anything, it highlights the impersonal grandeur of nature, which creates such extraordinary phenomena without awareness or design. The concept of time inside a black hole remains one of the deepest mysteries. What does time mean when all paths lead inevitably to the singularity? Inside the horizon, the roles of space and time are reversed in a sense. Moving toward the singularity is not a spatial choice, but a temporal inevitability. You are not moving through space to the singularity, but moving through time to it. This inversion challenges our deepest intuitions. We think of time as something that flows around us, carrying us forward while we move through space. Inside a black hole, this framework collapses. Understanding this requires abandoning familiar concepts and embracing the abstract structure of space-time revealed by Einstein's equations. It is a place where language struggles, where diagrams and mathematics speak more clearly than words, where the mystery of time itself is laid bare. Future civilizations might use black holes as energy sources and gravitational anchors. If humanity survives for millions or billions of years, black holes could become valuable resources. The Penrose process could extract rotational energy. Matter falling into an accretion disk could power vast stations. The intense gravitational fields could be used for time dilation, allowing relativistic journeys into the future. Black holes might anchor megastructures, provide stable gravitational environments, or serve as waypoints in a galaxy-spanning civilization. These speculations are far-fetched by today's standards, but they illustrate that black holes, despite their dangers, also offer opportunities. They are not merely objects to observe from a distance, but potentially useful phenomena. Of course, such utilization would require technology far beyond anything we currently possess, and the risks would be immense. But in principle, black holes could be tamed, their power harnessed, their properties exploited for the benefit of advanced societies. The ultimate question of what lies beyond a black hole singularity remains open. Does the singularity mark an absolute end, a place where space-time terminates? Or does it connect to something else, a new region, a different universe, a bounce into a new epoch? Current physics cannot answer this with certainty. General relativity predicts an end, but general relativity also predicts its own breakdown at that point. Quantum gravity, when fully understood, might reveal a different picture. Perhaps the singularity is not a point, but a region of extreme quantum fluctuations. Perhaps information re-emerges in some form. Perhaps there are structures beyond our current capacity to describe. The singularity is a placeholder in our theories, marking where known physics stops and the unknown begins. It is a frontier, and frontiers are always where the most exciting discoveries await. Black holes are gifts to humanity from the universe itself, challenges to our understanding. They present us with puzzles that force us to refine our theories, to push the boundaries of what we know. Every black hole observation, every theoretical insight, every gravitational wave detection adds to our collective knowledge. They teach us about gravity, time, quantum mechanics, and the structure of space-time. They humble us, reminding us of our ignorance, while simultaneously empowering us with the knowledge we have gained. In studying black holes, we are engaging in one of humanity's noblest pursuits, the quest to understand the cosmos. This quest defines us as a species, setting us apart as creatures who not only live in the universe, but seek to comprehend it. As our understanding deepens, black holes become less alien and more familiar. The first physicists to encounter black hole solutions found them bizarre, impossible, hardly believable. Today's physicists work with black holes as routine objects, calculating their properties, predicting their behavior, comparing models to observations. This familiarity does not diminish their wonder, but changes its character. They are no longer incomprehensible mysteries, but explicable phenomena, strange yet understandable. This progression from alien to familiar mirrors the history of science itself. What once seemed magical becomes mechanical. What once inspired fear inspires curiosity. And in that transition, we gain power. The power to predict, to manipulate, to incorporate the once unknown into our expanding sphere of understanding. Black holes are becoming known, and in becoming known, they are becoming ours. And now, dear traveler through the mysteries of the cosmos, our exploration draws to its natural close. You have journeyed with me through the strange and beautiful landscape of black holes, from their formation in the depths of stars to their role in shaping galaxies, from the event horizons that mark points of no return to the singularities where space-time itself may end. You have glimpsed the mathematics and the physics, the observations and the theories, the questions answered and those still open. Black holes stand as testament to the universe's capacity for extremes, for beauty, and for mystery. They remind us that reality is stranger and more wonderful than we can easily imagine, that the cosmos holds secrets we are only beginning to uncover. As you rest now, let your mind drift among these dark giants scattered across the universe in their patient silence. Picture the glowing accretion disks, the invisible event horizons, the warped spacetime surrounding them. See the gravitational waves rippling outward from merging pairs, carrying news of collisions across billions of light-years. Feel the weight of deep time, the billions of years these objects will persist, outlasting everything we know. Let these images carry you gently downward, like matter spiraling into the accretion disk, around and around, slower and slower, until you cross your own threshold into the peaceful darkness of sleep. The black holes will continue their watch, spinning silently in the void, indifferent to our wonder but offering it freely to those who seek. They were here long before us and will remain long after. They are monuments to the power of gravity, to the inevitability of collapse, and to the enduring mystery of existence itself. In their darkness, we find light, the light of understanding. In their silence, we hear the universe speaking its deepest truths, and in their patient waiting, we find an invitation to look closer, to think deeper, to never stop asking why. Sleep now, knowing that the universe is vast and full of wonders. Black holes spin in distant galaxies, event horizons mark invisible boundaries, and space-time curves and flows in the cosmic dance. All of this continues while you rest, the great machinery of existence turning without pause. You are part of this cosmos, made of stardust, connected to everything through the deep laws that govern all. As your consciousness fades, you join the universe's rhythm, resting as the black holes rest, existing as they exist, patient and timeless and still. If you are still awake, you may continue to the next video when you are ready. But if sleep is calling, answer it. Close your eyes, let go of thoughts, and sink into the darkness that waits behind your eyelids. It is not the darkness of black holes, but the darkness of rest, of peace, of the quiet place where the mind stops and the body heals. Tomorrow, the universe will still be here, with all its mysteries waiting. For now, there is only sleep. Good night, rest well, and may your dreams be as vast and wondrous as the cosmos itself.